Welcome back to Physics 340. I'm Dr. Dave, talking to you today about the Taylor series. I need to apologize before we get too far into this. I've attempted to record this video 4 times now, making it to the end each time, and I've always had a problem at the end. So if I seem to skip over things or maybe not be as clear as I might be in other cases, please understand that that's why. Okay, so the big takeaway point of the Taylor series is that it can sometimes be difficult to use a function as given, or the interpretation of a result might be unclear. So enter in the Taylor series. The Taylor series is basically an attempt to make solutions or functions that you're working with look like other functions that you know. So what is the Taylor series? Well, technically speaking, it is an infinite series in which you take some function x and you replace it by a polynomial function. And this polynomial function has powers of x, x squared, x cubed, all the way up to, x to the infinite power. And formally, this function is finite if you take, this function does converge to the exact answer with an infinite number of terms. However, in general, anytime you get up to x to the fifth or x to the sixth, like the fifth or sixth term of the Taylor series, you're going to be close enough that you won't be able to tell the difference anymore. And this is really just a warning that if you ever try to fit something with a polynomial and you get to the fifth or sixth power and you think, wow, that's a great fit. I can't believe that this is x to the fifth. What you're really seeing there is you probably found the Taylor series approximation, not any actual true behavior. So stick that in the back of your brain. If you ever do curve fitting and you get a fifth order polynomial and you think it's amazing, it's probably the Taylor series that you found, which is good, but it's not some fundamental thing. So speaking from the voice of experience. So let's consider that we have some function f of x. It looks something like this. Well, if we want to expand that function around x equals a, this is our region of interest. And if we look at that, we say, oh, well, that's kind of quadratic. Meaning anytime we get something like this, we go, ooh, that's a line. And we go, oh, that's a U shape. That's a quadratic. It's not a quadratic, right? If the function goes back down like this, that means that's like x to the fourth, and that's like x cubed or something. It's got some asymmetry around the well. This is not a simple quadratic function. However, in the region of interest, that looks like a u. That means it looks quadratic, and we're going to try to make it be quadratic. So, again, I want to point out that the exact form of f of x is probably quite complicated. And so that's when we want to use a Taylor series. Okay? So if we just look at the form of the differential equation, the Taylor series is some value that we start with, some f of a, and then it has a linear term, and then a quadratic term, and then a cubic term, etc. It's basically the construction of a polynomial with derivatives evaluated around the point you're expanding as coefficients. And just as a quick sanity check, if you do your Taylor series and you plug in x equals a into your function, you're going to get all of the polynomial behavior to vanish. And that's what you want to happen, sort of a visual error check at the end of your problem to make sure you've done that correctly. So there are two forms of the Taylor series. They're not actually different from one another. It just depends how you're looking at the problem. The author of your textbook, Taylor, on page 75, introduces this form of the Taylor series, which probably looks different than what you would have seen in Calculus 2 and can seem pretty confusing because he doesn't really define his terms. He says f of x plus delta. Well, if I'm looking at that, I'm still thinking that x is my variable, but that's not what Taylor means. Taylor is expanding around some value of x, which he's treating as a constant. So in the general form of the Taylor expansion that you would have learned in Calculus 2 and other physics courses, you would have written f of a. Taylor writes f of x. So once you realize that he's just treating x as the constant, it's not such a big deal. So then you continue on and you see, oh, okay, now this looks like the Taylor series I've seen in prior courses. But what about x minus a and delta? Those aren't the same. Well, all Taylor's really doing there is as follows. He says, okay, I have some function, I'm expanding it around x, and I'm going to go, out to here, which is some delta away. I'm going to go out to here, which is minus some delta away. So he's just treating delta as how far away you are from the point of expansion. So he's basically just changing his coordinate system. So instead of using the old coordinate system x minus a, He's just using delta to say how far away am I around the place I'm expanding about. The quick and short version is use this form of the Taylor series until you really get what you're doing, and then you'll probably use this form, but this will always get you the right answer and lead to fewer problems in the end. So just to be clear, what are we doing? We're writing a polynomial approximation of a complicated function that we're not sure what to do with, and we're determining the coefficients by values of the various derivatives. All right? So let's look back at our function that we want to do. So we have some sort of original flavor function. It looks something like this, and we want to do a Taylor series around a place that we have good agreement. So we're just approximating something with another thing. So technically speaking, you do an infinite number of terms, but that's too much, right? A Taylor series will give you an actual function as long as it's well behaved, but you don't need that. In general, we're going to use a Taylor series only when it makes our life simpler, and only when we want to approximate some part of the function to find out the answer that we have. We're going to do an exact example here at the end, but I just wanted to sort of build up what we're after. Okay. So I've mentioned to you how the textbook treats the formula for the Taylor series a little bit different than what you would have seen in Calc 2, and I just want to sort of illustrate that out a little bit more. So in your normal Taylor series, you're normally just still keeping your original x coordinate. So when you're out at this point, checking your value here, x is equal to a plus some distance away, a plus delta. So this is actually what Taylor is doing, whereas I left this a to sort of keep that connection there. What Taylor is really doing is he is putting basically his coordinate system here and asking about distance away left or right. So again, his x minus a becomes delta, x minus a becomes delta squared, right, etc. So it looks weird, it looks different, but it really isn't any different. All right, let's look at a real example to actually do this. Let's imagine that we have f of x equals ln of x, and we want to expand around x equals 1. Why do we want to do that? Well, f of 1 is equal to 0. That's this part of the logarithmic curve right there. And so we're going to ask ourselves, what is the approximate solution to ln of x around this region? Why? Well, no one likes logs. We burn them for a reason. So we want to come up with some approximate form and not use the log if we can avoid it. So we're going to do an expansion around where? Around 1. All right. So the first thing you do, if you hear Taylor series, you should think start taking derivatives. All right, let's get at it. So f of x is ln of x. So f of 1, which is our point of expansion, is ln of 1 is 0. The first derivative is 1 over x. The first derivative evaluated at 1 is 1. The second derivative is minus 1 by x squared. Evaluated at 1 is minus 1, and so on. So when you hear Taylor series, start pounding derivatives, plug it in. So now we go, excuse me, to our form of right here, and we're going to plug in f of 1. We get that. We're going to plug in f prime of 1. We get this, f double prime of 1. Now you get a 1/2 instead of just a 1, because the Taylor series does have this factorial term in the denominator here. And just as a quick reminder, 0 factorial is a definition. It is a definition of equals to 1. And the reason we use that definition is we don't want to write the extra term in front of the sum. All right. So once we plug in all of these terms and we simplify, we get a polynomial expansion that looks something like the following. Now, one thing to understand in this polynomial expansion is you haven't gotten all of your powers of x, right? When I expand out these various terms, x minus 1, x minus 1 squared, x minus 1 cubed, you're going to pick up powers of x from each of those polynomials. So we really don't want to do that. Instead, what we want to think about is, how many terms do we need? We don't want to worry, do I have all my x terms and my x cubed terms? Because you're going to have an infinite number of those. However, because of the factorial coefficient, those further ones do become small pretty quickly. Okay. So now the question is, how good is this expansion? So now if I go, okay, what's f of x? Right, ln of x. What's f of 1.1? Well, I just plug in L of 1.1 and I get that. If we go up and we plug in 1.1 into our expansion, this is what we get here. And as it turns out, you see that you had x minus 1, right, terms, and then you had x minus 1 squared terms. Well, because we're expanding around 1.1, we see that the delta that Taylor was actually talking about is really just x minus a, which is 1.1 minus 1, which is just 0.1. So really, all Taylor's doing is sort of skipping a step to the end and saying delta, delta squared, delta cubed. I just wanted to point that out. It really isn't a different definition. It just looks different. So we plug in all of these, and this is what you get. So we see that this thing's great to 4 decimal places, and that 5th decimal place only varies a little bit. So our approximation of ln of x is really quite good at 1.1. Well, how about as we get further? At 1.2, you plug that in, you get 0.18232. The Taylor series out to the 3rd digit here gives you almost the same form again, right? We get 3 decimal places of exact values. So that's pretty good agreement. What about 1.5? Well, as you plug in those values there, you still have your first decimal right, and your second decimal is not that far off, but once you get beyond that, it begins to fall apart. So how far can we push the Taylor series? Well, if I go out to f equals 2, I get ln of 2, and I put on my Taylor series, and I no longer get what I wanted. Had I gone to, say, the 4th term or the 5th term, maybe I would have picked it up. But again, we're not hoping to generate a whole slew of polynomial terms, just a couple to give us an approximation of what our function looks like. So how far away can you move, or what can your delta be? Generally speaking, delta being much less than 1 is a good rule. So we see that 1.5 still works. I wouldn't go past a half away from where you're after. Again, it just depends what you're trying to do, and you check your Taylor series to make it right. So never really worry about which form of the Taylor series you're using. Just use the one that I provided, and you'll see that Taylor's form does work, but we'll get to it another time as to why that's really the better result. Okay. So now let's look at let's look at one more example, one slight different variation. So we just did a Taylor series of ln of x. Now let's do a Taylor series of ln of a plus bx, about x equals 0, with a and b being constants. All right. So what you get now, f of x equals this, right? Again, we hear Taylor series, we start taking derivatives. Plug in 0, you get ln of a. F prime is this, the first derivative gives you that. You plug in 0, you get b over a. Take the second derivative, this is what you get. You plug in 0, you get b squared over a squared, and the third derivative is as follows. You put that all together, meaning you say, okay, I have my polynomial expansion, and I'm going to plug in these terms. And here we go. We get all the terms from our derivative expansion. And that is our form of the Taylor series. And it is quite good, but it does bring up a possible problem. What do I mean by that? Well, we had just done a Taylor series of ln of x, right? F of x is ln of x. And we had done it around where? We had done it around x equals 1. And so let's just sort of collect that result to make sure we're clear of what we're looking at. So f of x, f of x is approximately equal to that, right? When we were looking at our ln of x function, okay? However, f of x, when we're looking at our other function, looks quite different. And the question is, can we use one to get the other one? Are these two forms equivalent to each other? And you might say, well, sure, because this is ln of a plus bx. So you might think, well, this is ln of x, and that's that. So why don't we just go ahead and take a equal to 0 and b equal to 1? that immediately gives us a problem. Well, why? Well, ln of 0 diverges. Putting a 0 in the denominator diverges. 0, right? We have a problem. What did we do? We did the expansion, right? We did the expansion of ln of x around x equals 1. We did the expansion of ln of a plus bx around x equals none. Not the same point. So if you want to make it look like the prior term, what you'd actually have to do is to take a equal to 1 and b equal to 1. So it would look like 1 plus x, and now your expansion of x equals 0 would work. Well, we think about that. Does it actually compare? If you put in a 1 here, this becomes 0. You put in a 1 here and a 1 here, that just becomes an x term. Put in a 1, these go away, you get an x squared term. And so now we're at least starting to get terms that begin to line up. And the Taylor series may not look perfect because the series expansion isn't unique. But you have to be careful. You can't just plug one formula into another. And if I've confused you by that, I would just go ahead and purge it from your mind for right now. Come back after you've done a few Taylor series problems, rewatch this section, see if you understand it. All right, so now we have this tool. Let's actually do a concrete example. Let's see what we can learn, if anything, from this problem. So imagine you had a particle bound in some kind of periodic potential. This could be a crystal, an electron moving back and forth, oscillating around. And let's just say that this potential is given by V naught cosine lambda x. And this is in energy units because it is a potential energy. And we could ask ourselves, all right, I don't like cosines. Can I instead use a Taylor series? Well, maybe. Using a Taylor series for a particle with energy E1 wouldn't be as good as using a Taylor series for a particle of E2. Well, why? Well, down here it looks quadratic, but up here it's not really quadratic because why? It's beginning to bend back over, right? So you could do a Taylor series up there, but it's beginning to bend back over and it's a little bit harder to understand, or at least you have to keep more terms in the polynomial. So generally speaking, when you're looking at like the bottom of a well, you say, oh, that looks quadratic. I'm going to get rid of cosine. I'm going to make it a quadratic, and I'm going to get my answer that I'm after. So we're going to ask the following question. What is the effective spring constant for a particle near the bottom of this cosine well? And you might say, well, what do you mean by effective spring constant? Well, let's treat it like a spring, right? If it's in this, it's going back and forth. It's feeling a variable force. That force depends on how far away from it is from the bottom. That sounds like a spring to me. You might say, Dr. Dave, the energy of a spring is a half kx squared. That's not cosine lambda x, right? Well, maybe it is. If I do a Taylor series here, maybe I will get something that looks like that. You know, spoilers, yeah, it does. Well, okay, what would I choose for my A? All we know is that at A, it's at a bottom. Well, we know more than that. We know that here, it's going to be minus V naught. So now the question is, what value of A actually gives me that? All right, well, I know that V of A is minus V naught, which is V naught times minus 1. And when do I get a minus 1? Well, when cosine is of argument pi. What is the argument of pi? Lambda A. So when lambda A equals pi, or when A is pi over lambda, that's where I'm doing my expansion around. So we go back and we do a Taylor series, which means we start taking derivatives. So f of x is this. We plug in our A, we get cosine lambda this, we get minus V naught. No big surprise, that's the bottom of our well. We take the first derivative, we plug in our value, and we get 0. What does that mean? Well, in a quadratic solution, when you have no x term, that simply means that your parabola is centered around where you've drawn it. What do I mean? What I mean by that we'll see at the end of the solution. F double prime, you take it and you get a value here. So we have now created a Taylor series expansion based on our cosine term. When we go plug in our terms, this is what we get. We get minus V naught, which is just a shift, and then we get a quadratic term here. So if you were back in high school, pre-calculus or something, and your professor put on a test, please graph the following function. Well, what would you have done? You would have drawn your coordinate system. You would have said, okay, I know that this minus sign means I go to the right because it's counterintuitive. Where do I go? I go to pi over a. So you say, okay, here's pi over a, or sorry, pi over lambda. That's my a. And I have a parabola now that's shifted downward by minus v naught. So you have something like that. And that is what your cosine solution looks like. So what do I mean by there is no shift? If you had an extra, the shift only moves you left or right. So the shift moves you over here or moves you over here. If the center of our expansion is at the bottom of the parabola, there is no shift term. All right, so what about the question about what is the effective spring constant? Well, we have now built a parabola for v cosine, sorry, this should say lambda x here, at the bottom, centered around pi by lambda. Okay. So the true function looks like this, right? This ugly cosine, and our Taylor series looks something like this, which agrees quite well near the bottom. So earlier I had called it omega, and I realized it was confusing and tried to make it lambda. All right, so what about stiffness values? Well, what do we have? We have U as a 1/2 kx squared. That's our standard expression for spring energy in the past. Well, that's looks just like that now, doesn't it? So now we have this being our displacement from the well. This term right here tells us about the spring constant. So just by pattern matching, K is that, lambda squared V naught. So what is lambda? Lambda is known as wave number. You might have encountered this in chemistry courses, talking about NMR, inverse centimeter units. Have you ever heard that? That's talking about your wave number. And low wave numbers tend to be waves that are really quite far spread out. And this is basically a spatial frequency. It's how many meters you go before it replaces or it repeats itself. And if you have a high wave number, that means that the peaks are much more compressed. So therefore, the slopes of the side are much higher. So if the slopes are much higher, that means the force, which is the derivative of the potential, is going to be higher. So therefore, your spring constant will be higher, and that's exactly the behavior that we get. I want to thank you for watching the video. I'm sorry again if it was a little rushed or abrupt or maybe felt like it was cut off in a few places. This is unfortunately my 4th time trying to record it, and hopefully my last.